Hello everyone and welcome. In today's video I'm going to talk to you about these, which are ceramic bearings, and how they stack up against these, which are steel bearings. So first of all, I'll go through some of the bearing basics. I apologise if I'm making you suck eggs, but it's worthwhile. And then we will cover some of the nitty-gritty around friction data. So what we have here is an Enduro ceramic bearing. Steel bearings are generally of the same manufacturing type on the external. The dimensions of this are, this is a 6806 bearing, so 30mm in the middle, 42mm across the outside and 7mm thick. This one is a fully sealed bearing. In order to get the seal out to see how this thing works, get a Stanley knife, a utility knife, and then prise from the inside outwards. Like that, and then the seal will come off. When you get inside the bearing, it's more difficult to see, but what there are something called balls, which everyone should be familiar with, and a cage, and that's not totally apparent on this size of bearing. So I'm going to get a bigger bearing to show you what it's like. So with the seals taken off the bearing, the internals look something like this. So they are the same as this, just on a much larger scale, so it's easier for photographic purposes. This is the inner race, so that's where if you were in a scenario where this bearing goes on a bottom bracket, that rotates. This area around here is actually the cage. The cage holds the balls in, so behind each of these are the balls. The cage on this end-to-end bearing is pressed and then riveted. So I don't know if you can just see, but there are some small rivets in between the balls. What is important to note is that on some bearings, especially the smaller ones, the cage material can be different. So on this NTN one, it is metal, pressed metal. On this Enduro ceramic bearing, the cage is plastic. Something that's probably not thought about that's fairly important is how the motion of a shaft inside a bearing actually works. So if the inner race is spun like it would be inside a bottom bracket, the speed of the inner race, which is where my index finger is considerably faster than the cage speed. So the cage speed is where all the riveted things are. I will show you an animation of that later on. Now what we're going to do in the interest of proper engineering is we're going to cut this bearing up to show you what the inner race, the outer race and the balls look like. So I have grinder in hand, let's begin. We've taken the bearing apart and these are the three segments that I've obtained. So this is the outer race, the inner race and the ball and part of the cage together. Let's start off with the ball and part of the cage. In a ceramic bearing, almost all of them, especially on bikes, are what are known as hybrid bearings. So in a hybrid bearing, this bit, which is the outer race, just so we go over there, so we get that in shot as well. This bit, which is this piece, is metal. The inner race, which is this bit, which is still flipping hot, which is that bit there, is also metal. The balls, which are what I've got in my hand, are the only bit that is ceramic. You should be able to see the two sides of the cage. So one side there, and the rivet going through. If I turn it over, you can just about make out the rivet through the middle, which is where I skillfully angle grinded through. So now with the geometry and sort of basics of the bearing over, what I will talk about now is why ceramic bearings have less friction than steel bearings, and it's all to do with something called Hertzian stress or Hertzian contact stress. The study of bearings and friction reducing products, moving shafts, gears and stuff is called tribology. What Hertzian contact stress, the man behind it, said was if you have two spheres, or two balls, and put them next to each other and push really hard, At a microscopic level, there is a point, an infinitely small point where the two touch. At that point, you have infinite stress. And in theory, that is true. In practice, what happens is one material deforms slightly around another. So if this represents the rock hard ceramic ball and my hand is the inner race, what happens is as I apply load, my hand deforms around the ball to almost cup it slightly. And that is what's happening inside a ball bearing. The inner race and outer race, so these two parts, or you look at the bearing, this bit and this bit, this bit and this bit, they will deform slightly around the ball to cup it. Friction loss in a bearing or ball bearing also comes from how round and how smooth the bearing is. The more round and the more smooth the bearing are, the less the friction loss. In this day and age, if you buy a quality bearing, the difference between a Ceramicspeed that's allegedly 200 times more round than an SKF bearing that's not, is not worth even worrying about. One of the tests I've seen on YouTube videos, up and down the search page, is where they get a bearing that's on a wheel or on a bottom bracket and just spin it like that and say, wow, look at my bearing, it spun for a minute, whereas my steel bearing only ran for 30 seconds. That is an absolutely crap test. The reason why it's a crap test is because the bearing is unloaded. If you take just a normal bearing with normal clearance and just spin it round, it's in a state that you would not have in real life. In order to replicate real life, what you have to do is apply some preload. I alluded to this earlier when I was talking about clearance. Now, preload, what it does is, if this is the bearing, I'm going to apply some load there across the inner race outwards. What that does is that stops the bearing from skidding. So if you're looking at the bearing there and I hold the cage, I can actually rotate the inside without the cage moving. Okay, I'm not doing it very well. There we go. Hopefully you can see that. When you have a free bearing that's just spinning, you could actually just be skidding. If it's skidding, then the interaction of the grease, the cage, and all of that good stuff is not happening. It's also a good way to destroy your bearings very quickly. What C3 clearance means is that you have to apply more preload. The actual force you apply in terms of preload will probably be the same, but the deflection you get in the inner race going towards the outer race will be different. I've explained why ceramic bearings have less friction, but the question needs to be asked, why isn't everyone on them? The reason, especially on a bike, the reason is fairly straightforward. It's cost. Ceramic bearings cost significantly more than steel bearings. They are not a commodity item. The other reason why ceramic bearings are not popular is because they may not be faster. And the reason for that is because the vast majority of friction inside a ball bearing does not come from the ball running on the inner and outer race. It actually comes from the bearing seal, which is the red thing here, and the type of grease that's used. So with all the mechanics, stresses, contact stresses, all that out the way, let's consider some hard data with some graphs and numbers. This first graph is the one that everyone really wants to see. So I took some 6806 bearings, spun them up to 90 RPM, and then calculated the power that was absorbed. In red, they are ceramic bearings, but we can split these into three distinct categories. First of all, the cheap Chinese eBay bearing. The power consumption on that was 0.5 watt per bearing. So just the bottom bracket alone consumes 1 watt. Then to the left, we have all of these contact seal bearings. So from the NTN contact at 0.26 through to the Enduro steel contact at 0.3, they are all in one group. And then to the left again, we have the non-contact seal bearing. So the Enduro ceramic 0.13 through to the NSK non-contact bearing 0.17. Again, they are in one group. The thing to get from here is the Enduro bearing is the fastest on test, 0.13 watts absorbed, versus the next best placed steel bearing, which was the NTN non-contact bearing, that was 0.14. But that doesn't tell the whole picture. If we go to this next slide, which is the bearing life, this is effectively the bedding in period of the bearing, and the red and the blue are NTN and SKF respectively. The red line is an NTN bearing which has a steel cage. The SKF bearing has a TN9 cage. Both, the power absorbed doesn't really increase much over kilometers, whereas the power absorbed by the Enduro bearing increases significantly, and that is due to the hard ceramic balls basically wearing the raceway away. If we come on to this next slide and talk about it, I went to NTN, SKF, NSK and also Schaeffler, which is on the next slide, about how they distribute friction losses in a bearing at low speed. So 90 RPM sinusoidal loading means that the loading occurs as it would in a pedal stroke, so it's not completely across one pedal revolution. It's for a quarter of a revolution, and then you get a dead spot, and then another quarter, and so on. But if you look at the data, it's fairly consistent across the three manufacturers. The majority of the friction, or the power absorbed, comes from the seal, so NTN's at 60, SKF's at 54, and NSK's at 58. Then the grease is around about 30%, and the 10 to 16% is in rolling friction. Schaeffler, which is INA FAG bearings, gave me some more detailed information, and they said the seal was 60%, the grease was 28%, and then they split the rolling friction down, and they said cage friction was 7%, ball deformation was 3%, and raceway deformation was 2%. So cage friction is the only element of friction inside a bearing where it's not a rolling movement, it is a sliding movement. So it's quite plausible that that's where most of the friction comes from. That's 7%. The ball deforming inside the cage is only 3%. So if you go from steel to ceramic, and the results show there's not much difference, and that's the reason why, because there's only 3% of the total deformation. With that in mind, what I did was I carried out a little experiment where I took the NTN bearing and the Enduro bearing and then proceeded to dismantle them. So out of the box, the NTN had 0.14 watts absorbed, the Enduro had 0.13. Then I proceeded to take the grease out of the bearings and replace it with oil. When we did that, there was a reduction for the NTN from 0.14 to 0.11, and for the Enduro from 0.13 to 0.11. So there is a noticeable reduction in power absorbed there. If you go a step further and pull the seals off completely, the NTN has a marked improvement, so it's 0.08 versus 0.1. So this ties in well with the data from Schaeffler, NTN, NSK, and SKF. We go on a bit further, and this is a projected power saving. So this one with a 0 over it is the datum point. So if you had an OEM bike off the shelf, FSA bottom bracket with green sealed bearings, 6806, some zip wheels with crack wheel bearings, a Shimano 105 group set, that's your datum. If you went and bought some eBay bearings, then you would spend money and end up having to pump in an extra 8 watts or 9.4 watts to maintain an average speed of 35 kilometers per hour. If you went the other way and bought some decent bearings, Timken, you'd save 2.6 watts, NTN LLU, so that's the best one that has fully sealed bearings, 3.9. This one, the FAG 2RS, is very popular amongst cyclocross riders, 3.1 there. Again, I've coloured the ceramic bearings in red. So the Ceramicspeed and Enduro, 5 watts, 5.4 watts is how much you would save. And over to the right hand side is dominated by steel bearings, so SKF RZ series, NSK VV series and NTN LLB series. All of those bearings you would save around 6 watts. The the bearings to go for here really are dependent on the next slide, which is the cost per watt. So the cost per watt is, if you were to change the wheels, the bottom bracket and parts of the drivetrain, how much it would cost you divided by the watt saving that you would get. So again, the red represents ceramic bearings. These ones on the left hand side, the eBay ones, if you spend your money you're actually making life worse, so don't. Timken worked out the most expensive of the steel bearings, 38.46, but really it's dwarfed by Ceramicspeed bearings. So if you bought Ceramicspeed, you would be spending £102, dollars or euros. There's not really that much difference per watt. Enduro will be 83 units of currency per watt. And then down here on the right hand side we have SKF, NSK and NTN. If you are in the UK, it's probably easier to get NTN. However, if you're in the US, and a lot of the people who watch this channel are in the US, you will probably find it easier to get NSK. Okay, there is a slight difference in power, but it's not noticeable, so I wouldn't worry about it. That data analysed, there is clearly a difference between NTN, NSK, Enduro and all these bearings, which isn't just the ball bearing hardness and type. When you take these bearings apart, the boundary dimensions of all of these is roughly the same. The internal geometry is different, and if you look very carefully, I've got an NTN on the right hand side. This silver one in the middle is an FSA bearing, and this one is an Enduro bearing. The cage design of the NTN bearing is pressed metal that's been riveted together. These other two have what's known as a snap-in polyamide cage, so it's made of plastic. The advantage with this plastic cage is you can take the cage out. That is the cage, and with that the ball bearings have gone everywhere. The problem with these plastic cages is they have more friction, and I think that is what causes the friction increase, especially at low RPM, compared to the metal cage which is in the NTN bearings and NSK bearings. The Enduro bearing is of a similar type to the FSA bearing. If we take that out, it's a very similar cage design to the FSA bearing. And the thing to note here is the FSA bearing actually has more balls, so the gap between the balls is reduced on the FSA bearing. So that is the difference. So the actual bearing ball bearing material has very little effect compared to the cage, and that ties in with the data that was provided from Schaeffler and also the testing of the bearings that I did. So at 90 RPM, which is pedaling speed, a metal cage is beneficial. I think it's more accurate and clearly reduces the friction level. More data from Schaeffler suggested that up to 1000 RPM, you're better off with a metal cage. So the basic conclusion from all of this is to do a few things. One is, don't bother spending your money on eBay bearings because it's a complete waste of time. They don't last long, the fit's not very good, which causes quite high power absorption and then leads to shortened life. The metal they use is not as good. Then we come on to the actual ceramic bearings and whether they're worth getting or not, and the short answer again is no, they are not worth it, because at the speeds that bicycle wheels, bicycle cranksets go at, there is no advantage. Ceramic bearings are designed for high speed and bicycle bearings are simply not high speed enough. The other thing to note is that ceramic bearings on bikes aren't truly ceramic, because the raceways are metal and it's only the balls that are ceramic. The vast majority of friction inside a bearing comes from the sliding motion between the cage and the balls. In the case of a ceramic bearing, a lot of them tend to have, well, certainly Enduro ones have a polyamide cage, and that increases the friction, versus NSK and NTN, which are probably the two go-to brands, which have metal cages, and it's much more accurate and more difficult for them to manufacture that sort of cage, which is probably why Enduro don't do it. Would I buy Ceramicspeed bearings? Absolutely no chance. They are extremely overpriced, and they have been shown to be poorer than their steel counterparts and don't last as long. So that is the conclusion of all of this. Thank you very much for watching. I really hope you enjoyed the analysis of the ceramic versus steel bearing debate. Please check out my website, which is hambini.com, and also hit subscribe to subscribe to this channel. And if you like the video, please hit like, and if you didn't, hit don't like. If you've got any comments, questions, or anything like that, please use the comments box below. Thanks, and until next time.